Welcome back, everyone, to Lesson 19 of the GD&T Master Course. Today's explainer is all about circular runout. If you've ever dealt with rotating assemblies, you already know that managing exactly how those parts spin is absolutely critical to the success of your entire design. Okay, let's dive right into this. Picture this real-world scenario. You've got a brake rotor fresh off the manufacturing line. You check the dimensional inspection report, and hey, it says the part is perfectly round. The diameter is absolutely spot on. But the moment that rotor gets mounted onto a vehicle and you hit highway speeds, it causes massive, teeth-rattling steering wheel vibrations. So why does that happen? Well, it's because a feature being purely round in its form doesn't actually guarantee it rotates cleanly around its functional center. If that deviation falls outside your rotational tolerances, the fabricated part is basically unusable. That vibration leads straight to premature wear on your brake pads, severe assembly degradation over time, and just a miserable experience for the driver. That destructive wobble right there, that is the exact problem we're solving today. Here's our roadmap for this explainer. We'll start by understanding circular runout. Then we'll get into datums and tolerance zones, followed by measuring circular runout, comparing runout to other controls, looking at real-world industry applications, and wrapping up with some common mistakes and a review. All right, Section 1, Understanding Circular Runout. Let's shift away from our vibrating brake rotor for a second and introduce the GD&T concept actually designed to fix it. According to the ASME Y145 2018 standards, circular runout is defined as a two-dimensional measurement of deviation in a part's surface when it is rotated a full 360 degrees around a central datum axis. Simply put, it measures the wobble. It evaluates just a single circular cross-section at a time. Now, when you're looking at a machining print or an engineering drawing, you'll spot this tolerance control right away by its very distinct symbol, just a single arrow pointing diagonally upward. Whenever you see that arrow, you instantly know the designer is explicitly controlling how that feature behaves relative to a rotating axis. What's really interesting about this slide is how these controls directly impact the physical performance of rotating assemblies. These controls brilliantly bridge that massive gap between a static CAD model and real-world reality. Circular runout exists primarily because rotating parts absolutely must function smoothly in service. By controlling that functional rotation, we directly reduce dynamic vibration, which, you guessed it, solves our brake rotor issue. But it goes way beyond just brakes. It ensures proper bearing performance by preventing uneven loading on ball bearings, which would otherwise literally tear an assembly apart at high RPMs. It's also absolutely crucial for evaluating dynamic balance constraints. When parts are spinning at thousands of revolutions per minute, centrifugal forces amplify every single tiny physical deviation. Controlling circular runout restricts that natural tendency to shift or wobble, guaranteeing your center of mass stays right where it needs to be. Moving right along, Section 2, Datums and Tolerance Zones. Now, we have to talk about the absolute foundational element of runout, because without it, the control just doesn't work. Runout is literally meaningless without a stable reference point, and that reference point is your datum axis. Establishing this axis happens in a very specific logical progression. First up, the designer has to carefully select the functional datum feature. This needs to accurately reflect how the part actually assembles or functions in its final environment. Second, we establish the datum feature simulator. Out on the shop floor, this isn't some theoretical concept. It is the physical chuck, collet, or precision V-block that's holding the part. Why is this physical simulator so absolutely vital? Well, because a theoretical axis is perfect, but a manufactured part never is. We've got to derive a perfectly straight datum axis from that physical simulator so our surface measurement actually has a flawless center point to be evaluated against. So, in action, what does this look like? It looks like a tolerance zone of, say, 0.1, constrained directly around datum axis A. As the physical part rotates, the median points derived from that surface must all lie perfectly within that specified 0.1 tolerance boundary, relative to datum A. Remember, it's a single circular cross-section evaluation. You aren't sweeping the whole cylinder at once here. You are checking one specific slice. And it's not just about the surface being smooth. It's about its direct geometric relationship to that specific center of rotation. If the part is shaped like an egg, it fails. If the part is perfectly round, but its center is totally offset from datum axis A, it also fails. The surface has to be both round and correctly centered. All right, let's get into Section 3, Measuring Circular Runout. Let's take this out of the theoretical tolerance zone on your blueprint and look at the practical reality of a shop floor inspection. The true beauty of circular runout is how wonderfully straightforward the physical inspection method is, especially compared to checking pure form. Step 1, you mount the part on a precision spindle using that datum feature simulator we just talked about. Step 2, you set a dial indicator contact point against the circular surface you're evaluating, and you zero it out. Step 3, you just rotate the part a full 360 degrees. And finally, step 4, you simply evaluate the total indicator variation, which is the absolute maximum and minimum readings on your dial. If the total movement of that needle stays within the tolerance specified in your feature control frame, boom, the part passes. Now, while traditional dial indicators are standard, it's worth noting that modern quality labs also heavily utilize coordinate measuring machines, or CMMs. These use highly sensitive scanning probes to digitally plot the median points of these circular cross-sections and calculate the runout mathematically. Grounding this in reality, here you can see metrology tools being actively used to evaluate a component. While static measurements, like, say, using digital calipers to check a dimension, tell you if a part is the right size, a true runout inspection relies on physical verification using rotary equipment to confirm its actual rotational intent. You lock that central bore onto a precision spindle, drop your dial indicator onto the outer surface, and spin it. This dynamic setup guarantees that the actual manufacturing outcome strictly matches the functional dynamic intent of the component when it finally goes into a live machine. Which brings us to Section 4, Runout versus Other Controls. So the crucial point here is the technical distinction between circularity and circular runout. Circularity, which is often just called roundness, controls only the form of a feature. It is completely independent of any datum. It's basically just asking, is this cross-section a perfect circle? You could totally have a part that is perfectly circular, but its center might be completely offset from the rest of the part. Circular runout, however, controls that form relative to a specific functional datum axis. It asks, is this shape a perfect circle, and does it rotate perfectly around our chosen functional axis without wobbling? You use circularity when you only care about the shape itself, but you mandate runout when that shape actually has to spin around a specific centerline. Let's look at another fundamental comparison, true position versus circular runout. True position is fundamentally a locational control. It defines how much a feature's static position can vary from its intended perfect coordinate, often using the location of other features to set relative controls. Circular runout, on the flip side, is a dynamic, rotational control measuring surface deviation during active rotation. Listen, one of the absolute most common and costly industry mistakes is using runout when true position is actually what's needed. If a part only sits statically in an assembly and never actually spins, applying a runout tolerance just forces the manufacturer into complex, expensive dynamic inspection setups for absolutely no functional reason. So remember, choose true position when you care about where a feature statically sits, but you absolutely must choose runout when you care about how a feature behaves while actively spinning. Now, I want to point out a massive update in the engineering standards world. The ASME Y14.5 2018 standard actually eliminated the concentricity and symmetry symbols entirely from the GD&T language. No way, right? Why? Well, because they caused immense confusion and were widely misapplied across the entire manufacturing industry. Concentricity required inspectors to derive median points of diametrically opposed elements, which was incredibly complicated, time-consuming, and highly prone to error. In fact, a lot of organizations had actually banned the use of concentricity internally decades ago. Because of all that complexity, position and runout have now fully taken over as the absolute industry standard and preferred options for controlling coaxial features. If you need to control how two cylinders share an axis, runout is your definitive go-to tool. Let's jump into Section 5, Real-World Industry Applications. Mastering that single arrow symbol is incredibly important across so many critical manufacturing sectors. Let's look at a few examples. In the automotive drivetrain industry, applying circular runout to a brake rotor directly prevents that severe steering wheel vibration and uneven brake pad wear we talked about earlier. In electric motors, applying it to a motor shaft maintains dynamic balance at thousands of RPMs, preventing the motor from literally shaking itself to pieces. For industrial machinery or large fluid pumps, controlling runout on a bearing journal drastically reduces premature bearing wear, which extends the maintenance life cycle of multi-million-dollar equipment. And for aerospace wheel hubs, it ensures precise rotational alignment during extreme landing conditions. See, this one simple GD&T symbol has a massive real-world performance impact across nearly every mechanical discipline out there. All right, let's wrap things up with Section 6, Common Mistakes and Review. As highlighted by industry experts all the time, these are the frequent drafting and inspection mistakes you really need to avoid to prevent production delays and costly rework. First up, misidentifying datum features. If you pick a non-functional surface to base your rotation on, your runout measurement is entirely useless to the final assembly. Second, and this is a massive pet peeve for many experienced engineers, putting datums directly on theoretical centerlines instead of actual physical features. You cannot mount a theoretical centerline on a physical spindle. The datum has to be derived from a physical surface. Third, confusing circularity and runout, or just ignoring the rotational function entirely. Fourth, and this is crucial, misinterpreting indicator readings. Inspectors often mistakenly read the total indicator variation, or TIR, and confuse it with a simple radius check, accidentally halving or doubling the intended tolerance and incorrectly passing or failing critical components. And finally, confusing material condition modifiers, which just introduces total ambiguity into the inspection process. So, what should you really take away from all this? It's that circular runout is the definitive key to ensuring your rotating components don't just fit together, but actually perform flawlessly when in motion. It's the ultimate bridge between your design intent and functional reality. Circular runout ensures a single 2D slice behaves perfectly. But I want you to ask yourself, if a single circular cross-section can make or break a high-speed assembly, what happens when we need to control the entire surface of a cylinder all at once? Master the wobble to master the rotation. Next lesson, total runout, controlling the entire rotating surface.